Okay, going to look at some of these examples of integrals involving these log rules we had in section 5.3. Of course, we've got two rules, which are pretty common in this section and a lot of the rules. A basic rule and then a more complicated version that involves making a substitution. Okay, so of course the basic rule is the integral of 1 over x dx is the natural log of the absolute value of x plus c. Okay, and then this one, which is kind of a more general version where we have to make a substitution. Now, first of all, just something about this basic rule, the integral of 1 over x dx. If you wanted to, you could write this as the integral of x to the power negative 1 dx. And when we do that, a lot of people think, hey, we can use the power rule here, the one we had in the first section of chapter 5. Well, we can't, because the power rule came with this little disclaimer, something like, it works okay as long as the power isn't negative 1. Okay. If you try using the power rule when you have x to the power negative 1, it just doesn't turn out right. You get some kind of division by 0, it doesn't work. So we actually need a new rule for integrating x to the power negative 1, and now we have that. Okay. So remember, if you're integrating x to the power negative 1, you don't use the power rule, you use this rule. Okay, this log rule that we call it sometimes. Okay, so generally though, you probably won't use that first rule very much because it really only integrates one thing. It integrates the function 1 over x with respect to x. Okay, but if you look down here, this is the more general version, and what it allows us to do is kind of suggests to us that we can make a substitution. If we're integrating some fraction, which we can write as a denominator of u, so we call the denominator u. If the numerator turns out to be the derivative of u with respect to x, what we're really doing here is we're integrating 1 over u with respect to u. Okay, which these last two steps look exactly like the first rule, but with a different letter. Okay, so it's kind of suggesting to us under certain circumstances you can have a more complicated function to integrate, make a substitution, and then use this first rule. Okay, so that's probably the one you're going to use most often. You'll notice when you need this rule because you have a fraction under the integral sign, and the denominator is anything other than just x. If it's just x, we can use the first rule. Okay, but here it's not. So we're going to have to call u 6x minus 5. Okay, and that's the only choice we can make in this substitution. What it is we call u. Okay, so I'll go ahead and write the integral in a minute, but part of this substitution is to replace something under the integral sign with u, and to replace pretty much everything else with du. Okay, and du, if I just group these two terms together, what I can do here, if you would like, you could write the rule this way. It's really 1 over u. I can take that du dx and move it out as a factor by itself, times dx, and of course that's what we always call du. And that's what I have over here. Okay, so in other words, what I need to do is compute du and make that replacement. So I just get 1 over u du inside the integral sign. Okay, so du is the derivative of u with respect to x. Okay, what's the derivative of 6x minus 5? Okay, well, it's just 6. Okay, times dx. Okay, so here's what we got. We got the integral of 1 over u. And what we'd like to have here is 6 dx, because then we could just write du. Okay, but we don't have that, we just have dx. Okay, well, what do? Well, we multiply by 6, okay, and that's okay as long as we multiply by 1/6 right next to it, okay, because we know these two things will cancel. Okay, but as always, we don't cancel them, we take the one that's not something we need and we factor it out. So we've got 1/6 times the integral of 1 over u, and then once we do that, all we have left is this stuff, which is du. Okay, so look at what we get. 1/6, and now we can use the rule. And the rule says the integral of 1 over u du is natural log of the absolute value of u plus c. Okay, so that's 1/6 times the natural log of 6x minus 5. I've got to replace u with what it was originally chosen to be. Okay, so making that substitution, we got the second rule to work, and everything's okay. Okay, well, let's look at one more here, maybe a slightly more complicated one, but really it's the same exact rule we just used. Might be a little bit harder to see. you look at this one and you say, okay, we're integrating a fraction, no other rule comes to mind, so we got to do something here. Probably make a substitution. Since it's a fraction, if we're going to use that log rule, we need to call the denominator u. Okay, so we'll start with that. Okay, that's u. Okay. Well, what does du have to be? Well, du is always the derivative of u with respect to x times dx. Okay, so what's this derivative? It's the derivative of u with respect to x will be 2x plus derivative of 6x is 6, and the derivative of 7 is 0. Okay, so that's du. Okay, so far so good. Now if you look at what we have, we don't quite have this. We've got 1, I can write it this way, 1 over x squared plus 6x plus 7, and then just to kind of keep these things together, x plus 3 times dx. It's always okay to take a factor from the numerator and bring it out front as just a regular term by itself. And if you look at what we have, we're really pretty close right away. We've got certainly the most important thing, 1 over u, right? That's just u, okay? But du is 2x plus 6 dx, and what we have here is x plus 3 dx, okay? Well, again, it's actually a pretty easy fix because we sort of got lucky here. Okay, what we need is 2x plus 6 dx. What we have is x plus 3. Well, guess what? If you multiply that by 2, I can distribute this 2 inside and I'll get 2x plus 6. And it's okay to multiply by 2 as long as I multiply by a half as well. And of course, that 1/2 will just factor out. It's a constant, so we can do that. But if I leave that 2 here, I can distribute it inside and leave 2x plus 6 dx. Okay, and now if you look at what we have, we've got 1/2 times the integral of 1 over u du. Okay, we didn't have it to begin with, but we did this little multiply and divide trick, and now we've got exactly what we want. So this is 1/2 times the natural log of the absolute value of u plus c. Okay, so I just used the new rule to integrate the 1 over u du, multiplied it by a half, and added c. And of course, that's 1/2 times the natural log of what u was, x squared plus 6x plus 7, it's all in absolute value, okay, plus c. Okay, that's my indefinite integral. Now I think it's maybe important to mention that the problems we're doing here, they are specially chosen. I guess it's probably the nicest way to say it. They're chosen so that this rule will work. If we had had a very similar problem, but the only difference, let's say, was we had x plus 2 in the numerator, okay, right here we would have had x plus 2 dx. Well, guess what? If you multiply that times 2, you would just get 2x plus 4. Okay, so we'd still be off. If this had turned out to be something other than x plus 3, we might not have been able to multiply it by a number to get 2x plus 6. That's the key when you make substitutions like this. If you're off by a constant factor, that's okay. But if it takes more than just multiplying by a constant to get that last term to match up with the differential of u, then you've got trouble. So, it would be very easy to write down a problem which looks almost identical to this, but everything didn't work out quite so perfect. So, again, on these problems, you kind of get lucky sometimes. They're chosen so that these rules work. If the rule doesn't work, we'd have to resort to something else. And of course, there are a lot of rules of calculus which we haven't talked about yet. So there is hope even for the ones where this substitution doesn't work. But for now, we're okay.